right, so luckily one of you, at least one of you, read the chapter, and so you knew what to do when you got hit the snag, right? So let's just walk through it though. Let's pretend like we didn't know the little secret that we're going to reveal in a moment. You guys already know it, but let's pretend we didn't know. We start off saying that our domain is all integers. Now I saw a couple people make a predicate that said x is an integer. P of x, where x is an integer, or let P of x be x is an integer. Nothing wrong with that. But you can simplify it by just changing our domain, right? So you have one less variable to worry about. So in our case, our domain is integers, and our claim now is that P, therefore Q. In other words, 3n plus 2 is odd, therefore n is odd. That is our claim. So remember, in a proof, this is the known thing, right? We know the P to be true. If we didn't know the P to be true, who cares, right? Our proof is only in the event that P occurred, right? So in the event that we have some odd number, well, we have 3n plus 2 being odd, therefore n is odd. Okay, so that's what we're trying to do. All right, so here's our proof. We start off with 3n plus 2. We're claiming that is equal to 2k plus 1. That is a given. Agreed? That's a given. Then we use algebra and we solve for n, because remember, we're trying to prove that n is odd. So if I could just solve for n, and n takes the form of 2k plus 1, I'm done. But it did not. Look what it took the form of. We get n is equal to 2k minus 1 divided by 3. Everybody agree with my algebra? Yeah? Everybody see the algebra? Yeah? So does that prove that n is odd? No, there may be some weird way we can continue manipulating that and see, but I don't see it. Okay? Now, let me show you a common mistake. I think I did see somebody do this. This is a very common mistake. I'm going to see if it's not on my slides, so I'm going to see if I can walk through it with what we have on the screen here. The common mistake is to assume that this is odd, and then that would be 2k plus 1, and then plug it in for the n right here. Right? You can't do that because the whole thing we're trying to prove is if this q is true or not. So if you assume that it's true, then you've defeated the purpose of the proof, right? So that's a very common trap that you could fall into. All right, so we get to this point and we get stuck. Since we're stuck, we need to try a different method. A direct proof did not work. Notice the title of the slide, indirect proof. Okay? An indirect proof is basically anything that's not direct. There's lots of different versions of that, right? Okay, this one we're going to look at is a proof by contraposition. Okay? So there's nothing else we can do here, so let's look at trying a new method, okay? And we're going to do a proof by contraposition. So when we take the contrapositive, what does that mean? P therefore Q becomes what? Not Q therefore P, right? So here's our claims the same. We haven't changed anything there. But now our new proof, we're going to take the contrapositive, and we're going to go not Q therefore not P by contraposition. So what does that mean now that I'm saying? What am I now claiming? How would I read that not Q, therefore not P? How would I read that in English terms?
If n is even, then 3n plus 2.
Yeah, if n, so that's correct. Let's break it down a little bit though. I'm claiming if n is not odd, therefore 3n plus 2 is not odd, right? Well, the word for not odd is even, obviously. So what I'm claiming is if n is even, therefore 3n plus 2 is even. Now the known thing is n is even. That is the known thing now, right? That's the thing on the left, all right? So thus if n is even, therefore 3n plus 2 is even. That's exactly what we were just saying, okay? Well, we know the definition of an even number, 2k, where k is some constant, so we're claiming that n is equal to 2k. Again, in the event that not q occurred, the thing on the left, okay? So that's the known variable. Now we can just plug that in because it's known. We know for sure that n is even. How do we know for sure? Well, not quite. It's a tricky question. The reason we know that n equals 2k, but how do we know that n is even for sure? The truth is we don't know, okay? But because we're doing a proof, we only care in the event that n is even. If n was odd, we're not doing the proof. We don't care. But because we're doing the proof, we only are looking at circumstances where n is even for sure. So all times that n is even, That's what we care about. So therefore, because we're doing this proof and we know that the thing on the left of the conditional occurred, then we know that n is equal to 2k. Make sense? All right. Plug in the known value, and we get 3 times 2k plus 2. Or algebraically, we end up with 6k plus 2, right? That's equal to 2 times 3k plus 1. And you can stop right there. Agreed? Why is that? Why can we stop right there? 3k plus 1 is some constant, right? I think I called it C in this case, yeah. So 3k plus 1 is some constant. Therefore, we have 2 times 3k plus 1 is the same as 2c, where c is some constant. You dig it? So what is 2c? Well, thus if n is even, then 3n plus 2 is also even. Right? So we took n being an even number. In the event that n was even, we plugged in an even number, bless you, and it resulted in 3n plus 2 being even. Right? We follow that okay? Yeah? Good? Questions? Okay? All right. Thus, by contraposition, if 3n plus 2 is odd, then n is odd. Because remember, the contrapositive is the logical equivalent of the original statement. Right? Fabulous. Questions? I'm glad I put those slides in there. They remind me to ask. We good? Okay, so that's a proof by contraposition. What you're going to find, I think it's my next slide here. Oh, to the whiteboards again? Really? Yeah, to the whiteboards. Let's do it. One more. Let's see. Hold on. How much time do we have? Okay, I'm going to leave it to a vote. You guys want to try it, or do you want to move on? Raise your hand if you want to go try it. Nobody? Come on. You guys are lazy, man. It's probably to our advantage to not do it because we're going to run out of time, and if we keep going, we can get through all the slides. I just hate to have you listen to me for 2 hours straight. It's ridiculous. But we did. Well, 5. Mr. Literal back there, 1 hour and 50 minutes, and we did get a 5-minute break while you guys were at the boards there. Okay, so let's just walk through this. Prove that if n squared is odd, therefore n is odd. Okay, our domain is all integers. So let's just kind of as a group think through this. What does this formula start to look like? If n squared is odd, that's our known thing, right? We'll start with our, oh man, we already got a contraposition there. I was hoping to walk through it the hard way first. I made these slides last night. You think I know what's on them. Okay, so what you'll find real quick, if you tried n squared is equal to 2k plus 1, well, we want to just solve for n at that point, right? So ignore what's on the screen for a minute. N squared is equal to 2k plus 1. That's our known thing. Well, if I want to solve for n, what could I do? Take the square root of both sides, right? So we end up with n is equal to plus or minus the square root of 2k plus 1. Everybody follow that? Well, plus or minus the square root of 2k plus 1 does not tell me if I have an even number or not. It doesn't tell me anything. So we see we we got stuck. Let's try a proof by contraposition, right? So we're going to switch it, and now we're claiming if n is even, therefore n squared is even. Everybody follow my logic there? Okay, that's a contraposition. So now we know that n is even. Well, what do we have to do now? If n's even, and I want to know if n squared is even, what do I do? Come on. Right, but if I already know that n is even, right, that's equal to 2k, and then I want to know that n squared is even, what do I do to n? Just square it, right? It's already even, let's square it and see if it's still even. That's it, okay? So n equals 2k, as you pointed out, Jared, and then algebraically we're saying n squared, because we want to prove that n squared is even. Well, n squared looks like 2k squared, which is 2k times 2k, which is 4k squared. I can factor out a 2, and I get 2 times 2k squared. Well, what's 2k squared? Some constant, right? Some constant, I think I called it c again, right? Okay, and that is the form of an even number. Okay, I rushed through that pretty quickly, but does that make sense? You feeling okay about that? Okay, so again, then our conclusion is that if n is even, then n squared is even. That is true. Thus, by contraposition, if n squared is odd, then n is odd. You got to write that out when you're doing a proof. Somebody who knows basic math should be able to follow your proof step by step and not be confused. Okay? Good, Art? We feel okay about that? Fabulous. Questions? Any questions about a contraposition? Okay, let's look at a couple other ideas here. Counterexample. This one is super easy, okay? It's going to take us 5 seconds to cover this, but I want to make sure I throw it out there, okay? Prove that every positive integer is the sum of the square of two integers, okay? So that pick some random number for a minute. My claim is that the number 10, for example, is the sum of the square of two integers. Is that even true? Yeah, so what, if I were to take the number 10, what two numbers could I square and add up to each other that equal 10? I can't even think of one.
1 and 3.
So 1 squared is 1, 3 squared is 9. Okay, good, so that does work. Good, okay. All right, so it does work for 10. Have we proven it? Have we proven that it's true for all numbers? Not yet. So what else could we do? Start small. If I started with the number 1, can number 1 be the sum of two numbers squared?
Does 0 count?
Sure.
So 0 squared is 1 squared.
Yeah. Good. How about 2?
1 squared is 1 squared.
1 squared and 1 squared. How about 3? Aha. Yeah. Cannot be done with 3. There are no two numbers that you could square and add together to get 3. So what's our counterexample? Find one counterexample. We did. It's 3. For more details on that, page 88, example number 14 in your textbook, okay? There's a little bit more about counterexamples in there, and it has a little bit more in depth how we got to that conclusion. But if you can find a counterexample, the end. Now, what you don't want to do is start going through numbers infinitely, right? And just like, oh, I'm at 150,000, I still haven't found a counterexample. No, you need to try different proof if you're going down that route. But if there's an obvious counterexample, then that's it, you're done, okay? And so what have we proven? We've proven this to be false, right? All right, so that's it. Counterexample, we're done there, okay? Okay, so this is the basic idea of how to walk through a proof. Step 1, or step 0, we'll call it. If a counterexample is not obvious, then you're going to try direct proof. If you try direct proof, if that starts to fail, which we saw with that first proof that we did on the whiteboard, right? It kind of failed. So then you try a proof by contraposition, okay? If that goes nowhere, maybe try a proof by contradiction, okay? What's a proof by contradiction? Anybody read up on that? A contradiction is this. I have a claim, and a direct proof's not working, a contrapositive proof isn't working, so I'm going to try to prove the opposite is true, okay? I'm going to try to prove the opposite of what I'm claiming is true. If, while I'm proving the opposite, what I'm looking for is some sort of mathematical contradiction. If I run into a mathematical contradiction, something where somehow 1 equals 2 or something like that, then I know that this is false. So if the opposite is false, then the original is true. That make sense? We'll see an example in a second. But conceptually, we feeling okay about that? Okay. So proof by contradiction. Step 1, try to prove the opposite of your claim to be true. If you succeed, then you've proven your original claim to be false, right? If I don't run into a contradiction when I try to prove the opposite and all works out and I prove the opposite is true, well, then the original thing is false. So either way, I've found my proof, right? All right. If, however, your proof creates a mathematical contradiction, then we've proven the opposite to be false, therefore the original is true. Dig it? Okay. So here we go. This is a very famous proof that's, you know, when you teach people about proofs with this method, this is one of the most common ones that they will show, okay? So we want to prove that the square root of 2 is irrational by trying to prove the opposite. Let's just start off. If I try to prove that the square root of 2 is irrational just by direct proof, where would you even start? What would you do? I mean, I don't even know.
Calculator.
But what is the square root of 2? It's 1 point something, something, something. Can that be represented as a rational number? How can you prove it mathematically other than just observing it on a calculator? Even then, I don't know that it's very clear. Okay, so we're going to try to prove the opposite. And let's see if that goes anywhere. You'd see quickly that contraposition is not the answer here. So, contradiction. I'm going to try to prove that the square root of 2 is rational. I'm going to say it is, right? So prove that the square root of 2 is rational, all right? So let's start off with this. This is our definition, right? The square root of 2 is equal to a over b, because that's a rational number, right? Where b is a non-zero value. Agreed that's a rational number? Yeah? So I'm claiming the opposite of my original statement. I'm claiming that it is rational. I'm also claiming that a over b is fully reduced. That's important for the proof. Okay, it's fully reduced. Meaning a over b is the lowest form that the fraction can take, right? So if it's the lowest form that the fraction can take, what do we know about at least one of those numbers, a and b?
One's a one.
Not necessarily. In terms of odd or even, what do we know? One of them has to be odd. Very good. If they're both even, then it can still be further reduced. You agree with that? Does everybody see that? Okay. What if they're both odd? Can they be further reduced if they're both odd? Not necessarily. 11 and 3, we can't really reduce that anymore. 9 and 3, you could reduce more. So what we know at least one is odd. They both might be odd, but guaranteed one of them is not even. Agree with that? If they're in the lowest form. Okay, so here's our premise. Let's move on. Algebraically, would you agree with those two statements? If I squared both sides of this right here, I would get this. Yeah? And then I could rearrange that right to that. Agreed? Okay. So look closely at that. If you're looking at that, the question is, what can we observe? What can we observe about that? 2b squared equals a squared.
You'd have to say that a squared is even.
A squared is even. Very good. How do we know it's even?
It's equal to 2 times constant.
It's 2 times some constant, right? B squared happens to be this constant. B squared could be k, it could be some other constant, whatever, but it's some constant. So we know that a squared is even, right? Now, if a squared is even, what does that tell us? What else can we determine about the letter a, the number a? Is a odd or even? A is also even, based on this mathematical axiom right here. These are 3 axioms here. Any odd number times an odd number will be odd. Think about it. 3 times 3, odd, right? 5 times 5, whatever. 5 times 7, odd. They're all odd. Any even number times an even number will also be even, right? 4 times 4, 2 times 6. Those are all even numbers. When you multiply an odd and an even, you get an even result, okay? The one we care about, we're interested in right now, is the middle one. If I multiply an even number times an even number, it will be even. Well, since we're squaring a number and the result was even, that means the 2 numbers we started with were both even because we're squaring it. So it's one number that's even, okay? So with that being the case, we know that a is also even based on that axiom, all right? So we can say a is 2k, where 2k is some constant. Would you all agree with that?
Yeah.
Okay. Am I boring you back there right now? Oh, man. All right, then. Okay, so now, I've just cleared up some of the notes and we kept the basic stuff there. So we've gone by squaring both sides. We get 2 equals a squared over b squared. We do some math, and we discover that a is 2k, where k is some constant. Okay, fabulous. Now, if we know the value of a, we can plug it in. Would you agree that that 2b squared equals 2k squared, right? All I did was plugged in a right here, right? That is the same as that. Agreed? Okay. Now, let's work that out real quick. Would you agree with that? 2b squared is 2k or 4k squared, okay? Would you agree with that? All right. What's the next step going to look like? B squared equals what?
2k squared.
2k squared. What does that tell me about b squared?
It's equal.
Yeah. What can we observe? Okay, b squared is even. Therefore, by the same logic we looked at a minute ago, b is also even. Now, we're done basically with the proof. Just put the pieces together. What can we determine now? Okay, this leads to a contradiction. What is the contradiction? Yeah, our original claim was that A and B were not both even, but we just proved that they are both even. Okay, so A and B are both even. That is a contradiction because our original statement was prove that the square root of 2 is rational. Well, this was our original claim, that A and B are fully reduced, which means that one of them is not even. All right? Therefore, we've proven that A over B is fully reduced and that A over B is not fully reduced. That's a contradiction. Therefore, this is false. The math falls apart. Therefore, the square root of 2 being rational is wrong. The opposite must be true. Okay? Thus, we have a contradiction, and then you can read the conclusion there. Okay? Due to the mathematical contradiction, we've proven that it is not rational. Okay? That's a proof by contradiction. We feel okay about that? All right. Questions? I feel like we're flying here, guys. We're doing okay. It's like a marathon here. This one only takes like 3 days to get through all this material, man. These PowerPoints really streamlined a lot more than I expected them to. So I'll have to resist the urge to get on the whiteboard, I guess. Okay. Oh, man. Really? Already? Sweet. I didn't think we'd get to this today. Okay. The hummingbird proof. This is in the book. What's not in the book is the actual proof. The book just is on the same section that has the lions drinking coffee proof. It just makes the premises and the conclusion, but it doesn't show you that it actually works. All right? So here's what we're going to look at. All hummingbirds, these are the 3 premises, these are things we know to be true. All hummingbirds are richly colored. No large birds live on honey. Birds that do not live on honey are dull in color. Based on those 3 things, we want to prove that hummingbirds are small, that's a valid conclusion based on those 3 premises. Now, just at a glance with our human brains, not our math brains, does that seem to be true or not? To me, it's not super clear. I'd have to like really sit and ponder that maybe to see if that's true.
I think it is just because you take 2 and 3 and almost add them together, and then it ends up that since hummingbirds are originally colored,
Yeah.
they're small.
Yeah, it seems true, right? And it turns out it is true. But to make sure, we're going to walk through an actual proof of this to make sure that it really is true, okay? But just imagine if we had maybe one more premise or a slightly different conclusion, how quickly this would be. I have no idea. I'm going to have to do a proof, right? You see that? And so this one's sitting on that fence right now. It's one we can look at and go, yeah, I think it's true. It seems true, but I'm not 100% sure. The lion's fierce coffee thing was obvious, in my opinion, but this one's not as obvious. Okay, so let's walk through this. The first step when you're doing the proof, let's make our arguments, okay? What's our argument? Well, our argument is that premise number 1 is what's on the board, then premise 2, premise 3, therefore conclusion is this. What do we do with that information? Yeah, we got to convert this into some sort of math, right? Propositions and predicates, right? Okay, so let's get our assumptions down too, okay? So let's just make a couple assumptions. That number 1, small is the same as not large, right? Because we have this thing that says no large birds live on honey. So we're going to define that as small, right? And is the opposite of large, not large, or is the opposite of large. And we're also going to use the phrase dull in color is the same as not richly colored, right? Just so we can use negation. And then number 3, our domain is all birds. Make sense? Okay, next up, we're going to go with what you said, which is look at our propositions and our predicates, all right? So let's start with this one. P of x is the statement that x is a hummingbird. That seems reasonable, right? Because our domain is all birds, all right? What's another predicate that we could have? Forget the variable, but just what x is what? Okay, we could have x is richly colored. What else? X is large. Okay, let's see what we got here. X is large, that's going to be our Q. Our R is, here's the one we didn't talk about, that X lives on honey, which on the previous slide we mentioned the honey, obviously. Okay, and I think we got one more here. X is richly colored. So those are based on the original statements we had, original three premises, right? We good? All right, so now we're going to convert all this into equations, okay? Look at our arguments. Premise number one, all hummingbirds are richly colored. All right, I'll give you the first one here, okay? All hummingbirds are richly colored, which means for all x in the domain of all birds, right? P of x, which is if x is a hummingbird, therefore that hummingbird is richly colored. That's our first statement. Do you agree that that defines premise number one? Okay, what's premise number two going to look like in a form of an equation? How about this? There does not exist, and we forgot to mention the negation a second ago, there does not exist a bird that is large and lives on honey. Does that work? Yep. All right, premise number three. What's that look like? Okay, so birds that do not live on honey are dull in color. Okay, so it's universal, and then what? For all birds in the domain of birds, if that bird does not live on honey, therefore that bird is not richly colored. And with our assumption that not richly colored is the same thing as dull, that fits. So what's our conclusion? Mathematically speaking. All hummingbirds are small. That means if you're a hummingbird, therefore you are small. Make sense? Okay. What P of x and not Q of x would mean for all birds, you are a hummingbird and you are not small, or you are small, which is not true. Not all birds are hummingbirds, right? Make sense? Okay. That's a tricky one. Okay, this is our argument. We haven't even started our proof yet. We just converted it into math. So this is our argument here. This is what we're claiming. We're claiming that if premise one and premise two and premise three are all true, therefore our conclusion is true. Our P is premise one, premise two, premise three, right? Our Q is conclusion. Okay, so here we are looking at it again mathematically. The English argument on the left, you can see the definitions above with our argument, and on the right is our mathematical argument. Does everybody understand that? We agree with it? Feel okay about that? Okay, so now at this point, I can erase from my brain all the premises, like the English words. I can erase all that crap from my brain. I'm just looking at the math now. That's all that matters, okay? So I'm just going to erase all that stuff and just focus on the math. And we're going to have a big, long, nasty 15-step proof here, okay? So let's think about what we need to do here. We're trying to take all three of these things and manipulate it into looking something like this, right? That's what we're trying to do. So what's probably one of the first things we're going to have to do with all those premises? Instantiate all three of them, right? We're going to use a universal, an existential, and a universal instantiation, right? Before we instantiate number two there, the not existential one, what should we do probably? De Morgan it. Whenever you see negation, De Morgan the crap out of it, man. Try to De Morgan it, okay? All right, very good. So let's walk through this. Here we go. Step one is our first premise, right? That's our first premise right there. I just copied it over, and we're going to universal instantiation, and we get that. Some bird named B. It's a big bird, right? Actually, big bird's not a hummingbird, so let's, I should have used W for, no, woody woodpecker is a woodpecker, not a hummingbird. Is there a famous hummingbird? I don't think there is. All right, this is Bob the hummingbird. Okay. P of B, therefore S of B. Do we all agree with that statement? Based on universal instantiation, okay? All right. So I've highlighted that because we're basically done for the moment with premise number one. We've reduced it down to as far as we're going to go in this case. Now, I will tell you, when I first worked out this proof, I had a lot of trial and error, just trying to manipulate different things and see where I could go, right, what I could get. And it was tricky, and I don't know that I came to that conclusion first. I may have come to different conclusions until I got where I needed to be. Okay, next up, premise number two. What did we say we're going to do to it? De Morgan it. So what's it going to look like after I De Morgan it? The first, just one De Morgan, one level of De Morgan. For all of x, not then the whole thing, right? So move the sign, move the line, flip the sign. Yeah, we're just going to move that, move the this little guy to right in here, and we're going to flip that to be a universal. Yeah? Okay, so move the line, flip the sign. Got it? Yeah, we're going to De Morgan it again, right? But that was just step one of De Morganing, yeah. So doing De Morgan again, you can, if in your head, if you want, work it all the way through, but I want to just walk through each step of it, right? So we De Morgan it once using the first law, De Morgan's first law for quantified statements. We move the line, flip the sign. Let's do it again, right? We're going to move the line again and look, and in this case, this is more like the break the line version of it, right? Because if you remember, typically when I draw it, I draw the line up here, like that's a line instead of this line over here. So ignoring that, right? And so if we look at break the line, I broke that line right there. And so that would put the line here and here, right? And ignoring those little negation symbols right there. And then I flip the sign from an and to an or, right? So it's still the same idea, right? Maybe distribute the line, right? Okay, that's one of the reasons I like putting the line above it all, because it's a little cleaner in my opinion. All right, we feel good about that? Yeah? Good? Okay, what can we do now? Instantiate it, okay? Universal instantiation, would you agree with that claim? That if it's true for all birds that there's not Q or not R, therefore it's true for one specific bird, any one specific bird. So let's go ahead and make sure that it's Bob the hummingbird again. It's the same bird. We're just picking some random bird, okay? Because it's true for all of them, so it might as well be true for this one. How do we know it's true for all of them? Because our premises are true. They're known things. And if they're not true, then I'm not doing the proof, right? The only time we do the proof is if the premises are true, right? Okay. So I think this is the last step what we're going to do with premise number 2. I might be wrong about that. No, one more. Okay, yeah. It's faded out before you could read it. Okay. This table on page 27 or whatever that I keep referring to, there's one more logical equivalence rule that we can apply here, which again, by trial and error, I discovered we needed to do this. Okay. So here's that rule. The rule is logical equivalence number 3 in table 7. It claims that if you have a something or something, it's the same equivalent as not something, therefore something. Dig it? Okay. So I had something or something, which is the same as not that thing, therefore not that thing. Agreed? That's based on that rule, logical equivalence rule, table 7 in your book. Okay. And the rule, you can see the rule right here. This is what the rule is, okay? I just copied it out of the book for you. Okay, so if I've done that, what's the next obvious step here? Yeah, by what logical equivalence? It's kind of a glaring one there on Q. Double negation, right? So, double negation, we now have Q of B, therefore not R of B, right? And this is where we're going to stop with that one, okay? So what I was trying to do when I wrote this proof, I knew that I needed a P of X ultimately, and I knew I needed a Q involved in the final solution. So I'm manipulating things to where I can get an isolated Q and an isolated P, and I kind of already starting to get there, right? I got a P here, I got a Q here, right? They're not quite where I need them mathematically, but they're there. So I'm thinking, okay, I'm going to stop reducing at this point, and let's move on to premise number 3. Follow? Okay. So, premise number 3. What do we want to do? Instantiate it, right? Universal instantiation, and we get, again, since it's true for all, it's going to be true for at least Bob, right? Bob the hummingbird. What else can we do here? Can you see anything? What can you see that's kind of, there's kind of a pattern here. If you look at line number 10, line number 2, and line number 8. Take a look at those 3 lines. It's not fully there, but it's kind of there.
You would be therefore not passive.
What do we call that? Hypothetical syllogism. Very good, very good. Okay, because you notice we have these, we have the same variable right here that we have here. And notice they both have to be exactly the same. They're both, if one of those was a not R and the other one was an R, they're not the same. They're 2 different things, but they are both the same. So by hypothetical syllogism of line 8 and 10, we can get our next step, which is Q of B, therefore not S. Okay? Now look what's happening here. Again, I needed that Q and I needed that P, right? I needed this and I needed this not Q. Well, I still have the P here and I still have the Q here, so why did I bother even doing this? Can you see what's happening there? Because I'm looking for a not Q somewhere. I need a not Q, right? That's one way to get a not Q, right? So if I did a contrapositive here, then and again, this is what was going on in my brain when I wrote this last semester. I need a not Q somewhere. Well, how can I get a not Q with what I'm looking at? I can do contrapositive, right? Okay, good. Okay, so here we go. Take the contrapositive. Now we get a not S, therefore not Q. So now I've got my not Q. Obviously we have a what problem there on the S? Double negation, right? We fix that real quickly. And now we're stopping there. That we've fully reduced premise number 3 to the point that I can now solve this riddle here. Do you see it? What is it? Line 2 and line 13, right? Hypothetical syllogism, right? And remember, the hypothetical syllogism just removes the middleman. I have P therefore S, and I have S therefore Q, right? I cut out the middleman. That is the same as P therefore B, or PB therefore not QB. Agreed? That is the hypothetical syllogism rule of inference, which was last lecture. And there we go, hypothetical syllogism 2 and 13. Now, what do I have? I have exactly what I was looking for, right? Look at that. I have a P and I have a not Q. It's exactly what I needed, right? Well, now, this is where we can instantiate, right? That's the obvious final step here. And why can I instantiate it? Because I've only proven it true for Bob. Sorry, generalized, thank you. I was saying the wrong one. But yeah, generalized, you're correct. Why can I generalize it? Because I've only proven it true for Bob. It's maybe a little misleading that I'm calling it Bob, because it's just some random bird, right? It's just some random bird. Doesn't matter what the bird was, who it was, it's just some random bird, some arbitrary bird. And when it's just some arbitrary bird, as you can see, no matter what letter I put in the parentheses there, this would have held true. No matter what bird I would have put in the parentheses, this would have held true. Therefore, it's true for all birds, because this is just some general arbitrary, non-specific bird, much like our 2K is some constant K, right? So because of that, I can generalize it, and since I can generalize it, I now have proven that this is the same as that. Yeah? And that's a full proof, and I've given each step along the way, every process I use, every rule, every rule of inference, every logical equivalence. We use logical equivalences, right? The double negation. We've used rules of inference, the hypothetical syllogism, and a whole bunch of other things. Okay? How do we feel about that? Okay, I think I had some other slides prepared in case we had time. Let me just quickly look at them. We got 3 minutes. We're not going to do them, obviously. I just want to see. Oh, that was the end. Dude, nailed it. Nice. All right, any questions about anything?